All right, good afternoon. Today we're going to be talking about section 3.3, rules for differentiation. And the motivation behind this section is that using the limit definition of the derivative is really cumbersome. You've seen this in homework 3.1, that plugging in f of x plus h minus f of x can be really, really tiresome. And then all of a sudden you've got this big long equation, and dividing it by h or factoring is just a real pain in the butt. So there's got to be an easier way, and in fact there is. And the easier way comes in the form of rules of differentiation. So the first one we've got is the constant rule. So if c is a real number, then d dx of c is equal to 0. Then we've got the power rule. If n is a non-negative integer, then d dx of x to the power of n is n times x to the power of n minus 1. So let's see what this looks like. I want you to evaluate the following derivatives. So go ahead and pause this video and see if you can't figure it out on your own, and if not, keep watching these videos if you'd like to see me do an example. So for this one, this very first one, we're going to use the power rule. And the power rule goes like that. And for n, we're going to let n equal 9. So d dx of x to the power of 9 is 9 times x to the power of 9 minus 1, which is the same as 9 times x to the power of 8. And we can do the same thing for d dx of x. But this time, n equals 1. So we get 1 times x to the power of 1 minus 1 equals 1 times x to the 0. And we know that x to the 0 is simply the number 1. So the answer is just the number 1. And finally, we've got d dx of 2 to the power of 8. And while it might be tempting to use the power rule, we know that we should use the constant rule because 2 to the power of 8 is just a number. So this one, using the constant rule, is just equal to 0. So let's keep going with a few more rules. Next, we've got the constant multiple rule, and this one is indeed different than the constant rule. But if f is a differentiable function at a point x and c is a constant, then d dx of c times f of x is the same as c times f prime of x. So let's do a quick example. Let me finish erasing this screen. I'm interested in finding d dx of negative 7 x to the 11 over 8. And we can use our constant multiple rule to pull out the negative 7 over 8. And then we're just left with finding d dx of x to the power of 11. And we know using our power rule that d dx of x to the 11 is 11 times x to the 10. We can simplify our expression and we get negative 77 x to the 10th over 8. And that's our final answer. Next, we've got the sum and difference rule. If f and g are differentiable functions at x, then d dx of f of x plus g of x is equal to d dx of f of x plus d dx of g of x. And this equation works if we use a minus sign too. So that's to say of f plus g is equal to d dx of f plus d dx of g. And the same is true for the minus direction. So f minus g is d dx of f minus d dx of g. So let's go ahead and do an example. I want you to determine d dw of 2w cubed plus 9w squared minus 6w plus 4. So our first step is to use the summation rule. And we get d dw of 2w cubed plus d dw of 9w squared plus d dw of negative 6w plus d dw of 4. Now I'm going to use the constant multiple rule. And pull out all those constants to in front of my differentials. So I get, oh no, I get 2 d dw w cubed plus 9 d dw w squared minus 6 d dw of w. And there's no constant to pull out here because this is just a constant. So this term goes to 0. And finally, we use our power rule. We get 2 times 3w2 plus 9 times 2w1 minus 6 times 1w0 plus 0, and in the next line I'm going to drop that. And finally, we simplify. And we get 6w squared plus 18w minus 6. And that's our final answer. So here's one rule for differentiation that's just completely different and is just thrown in here for fun. The function f of x equals e to the x is differentiable for all real numbers x. And d dx of e to the x is e to the x, if you can believe it. This one, there's no fun quote or anything like that to help you remember. You just have to remember it. And finally, we can always take a higher order differential or derivative. So if we assume that the function y equals f of x can be differentiated as often as we like, the second derivative of f is f double prime of x equals d dx of f prime of x. So you take the first derivative, and then you take the second, and then you take another derivative to get the second derivative. And in fact, we can do this many times as we want to. When we get to numbers, so if you can imagine, I could take f prime, f double prime, and even f triple prime. But after that, it gets a bit cumbersome to write. So we write f to the power of 4 in parentheses, and we do that on and on and on, which is how we get f to the power of n in parentheses. And that's what that means. We've taken n many derivatives, and that's simply equal to d dx of the f to the n minus 1 derivative. So let's see this in practice. I want you to find the third derivative of f of x equals 3x cubed minus 5x plus 12. Well, we have to start by finding f prime of x. We use our power rule and we get 3 times 3x squared minus 5. Now we're looking for our second derivative. We get 9 times 2 is 18 times x. And then for our third derivative, we're still using the prime notation. We just get 18, and that's our final answer. All right, I'll